Hello again, everyone. Now we will discuss representation of vectors in three-dimensional rectangular coordinates. So it is important to describe vector using rectangular components. And on the previous video, in the part 2 of our lecture series in statics of rigid bodies, vectors are not described in terms of their rectangular coordinates. They just have magnitude and direction relative to what is our preference. Now we will standardize the representation of vectors in terms of the three axes, which are the x-axis, y-axis, and the z-axis. So as we have discussed last time, vectors are efficient for analyzing three-dimensional structures. That's why we need to learn how to represent vectors in 3 dimensions. Now, this is the right-hand rule for the three-dimensional axis. It is important because we have to know the orientation of the positive axis. So in this case, if you use your right hand, and you may want to copy the hand in the figure, and the direction of the positive x-axis is as shown, and the positive y-axis is in the direction of your forefingers, and the direction of the z is along the orientation or the direction of your thumb. So this is important because if you try to rotate the axis, you should be consistent with the direction of the positive axis. So there you have the three positive axes. So if you rotate y-axis, make sure that you are not mistaken with the orientation of the positive z-axis and positive x-axis. The same case, if you want to rotate the positive x-axis, make sure the two axes are oriented in the positive direction properly. Now, as you can see in the figure, there are I, J, and K notations, which is what we call the base vectors. So, the bold-faced letter I, J, K represents the base vectors. So, this will help you in representing a certain vector in 3 dimensions. Okay, now if there is a certain vector in this image, let's say for example vector A, we want to represent that into 3 axes x, y, z. Now since we use the base vectors I, j, k, vector A is now represented or resolved into 3 components, which are axi, ayj, and azk. Now as you can see, there are 3 theta, or there are 3 ways of measuring angle of vector A. Now we have theta x, that is the angle measured from the positive x-axis. Theta y, which is angle measured from the positive y-axis to vector A, and theta z. That's why it is important to know where is the positive side of the axis. It's because you are about to measure the angle between the vector and the positive axis. Now, as you can see, we have here the direction cosine. So cosine theta x, later we will discuss why we use cosine instead of sine, and that is represented by lambda x. Cosine theta y is represented by lambda y, and cosine theta z is represented by lambda z, and that is the direction cosine. So to simplify the writing, we use the symbol or the Greek letter lambda. Now again, the vector A is represented in three axes, namely the AXY, AYJ, and AZK. So recall from our previous lecture, the resultant of these components is A. And if you add up the components, you get the resultant. Therefore, you represent A by adding up the component. But this is not the usual addition for algebra. So, vector is quite different because when you say you add, it doesn't simply add, but it gets the resultant of the components. Now, recall that AXI, AYJ, and AZK are the vector components of A. And as you can see, we have discussed from the previous video. So please watch the previous video if you missed it. So if vector E is the resultant of F plus G, no, this is represented in this way. Okay, so let's try to review our trigonometry. And from here, we can say that vector A is the sum of vectors AX and AY. So we have A is equals to AX plus AY. So the magnitude of each component of A can be determined by using direction cosines. So this is why we use cosine. It's because if you have a value of theta x and the value of A, you can have AX. And also if you have a value of A and theta y, you can get AY. So from these two equations, we can say that AX, or the component of A along the x-axis or along the positive x-axis, is simply the product of the magnitude of vector A times the direction cosine along x-axis. And simply, the y component of vector A is also the magnitude times the direction cosine of the vector measured from the positive y-axis. So this goes the same for a three-dimensional vector. So therefore, the magnitude of the z component of vector A may be derived from cosine theta z equals to az over A, which is similar to this 2. Therefore, it's also applicable for the z component of vector A using the direction cosine for theta z. So now, we can say that the vector has its component in 3 dimensions, and to get the component, it is simply the magnitude times the direction cosine. So there we have it. So let's replace the notation cosine theta x with lambda x for ease of writing. Okay, then we have the components written in a simplified form. We have ax is equals to a lambda x, and I'm sorry, this is y, and this is z. Now, to get the result or the magnitude of vector A, that is simply the sum of the square of its component, or the Pythagorean theorem. So we have the magnitude of A equal to the square root of the sum of its component, ax squared plus ay squared plus az squared. So again, vector A is represented as axi plus ayj and azk. Now the term I simply represents that it is, this component is towards the x-axis. J means that this component is towards the y-axis, and k for z-axis. And we can rewrite this in a form where we inject the direction cosine. So if we extract a, or we try to move out a from every term. So we have this equation rewritten to this one. Recall that the x component of a is also this one. The y component of a is this one. And the z component of a is this one. So if you try to see, this one is the unit vector, and this is the magnitude of the vector A. So we have discussed this one previously on the part 2. So recall that the vector A has magnitude, and the magnitude is this one, and direction, which is this one, the unit vector. So we come up with this formula. So yan. So that's it. Okay, now the unit vector now is in the form of this one. Lambda is equals to lambda xi plus lambda yj plus lambda zk. Okay. Now, because the magnitude of lambda is 1, or if you get the sum of its component, it is equals to 1. This property is also based from the unit circle in the two-dimensional analytic geometry. From the unit circle, recall that sine squared is the y component, cosine is the x component of the unit circle, and they have a hypotenuse equal to 1. Only that we use direction cosines in terms of lambda. Now, how do we add two vectors? So we already know how to represent vectors. Say we have two vectors. How do we add them up? So letting see the sum of vector A and vector B. We have C is equals to A plus B. So let's write vector A here and vector B here. Now let's add them up, and C could be written as C is equals to Cxi, the x component of C, the y component of C, and the z component of C. Now C, to get the x component, Cx, you simply add both the x components of A and B. So that's why this is Ax plus Bx. So for Cy, you simply add Ay plus By, and the same case goes for the z component. You simply add Az and Bz. Now we can say that Cx is equals to Ax plus Bx, Cy is equals to Ay plus By, and Cz is equals to Az plus Bz. So we have the summary here. So we have vectors A and B. Now adding them up, we have the components Ax plus Bx times I plus Ay Byj plus Az Bzk. Now to fully appreciate this one, let's have this figure. So when vector C is equal to vector A plus vector B, let's have a representation here. So vector A has two components, Ax and Ay, and the vector B has two components also, Bx and By. Now if you connect the tail of A to the tip of B, you get the resultant vector C, which has a component along x that is Cx. And as you can see, Cx is equals to Ax plus Bx, and the y component of C is equals to Ay plus By, which proves our method in adding vectors. So we have, again, it's okay. Cx is equals to Ax plus Bx, Cy is Ay plus By, and Cz is Az plus Bz. Now, there are some vectors which are not really drawn from the origin of the global axis. So when we say global axis, this is the our XYZ axis for all of our vectors. So some vectors are not really drawn from the origin or point O. Some of them are written somewhere or originates somewhere in the Cartesian 3D coordinate. So the vector drawn from the origin O to coordinate system to point B is denoted by OB. So a vector drawn from O to B is denoted OB and is called the position vector of B. Now, the vector drawn from origin O of a coordinate system to a point A, now this vector is denoted by OA, is called the position vector of A. Okay? Now, what if the vector is drawn from A to B? The vector is called, is represented or written in this manner, and it is called the position vector of B, but you have to add relative to A because it is drawn from A to B. So again, this is position vector of B relative to A. So the way you write it is, you can easily recall how to write this one because it is the origin of the vector to the end of vector and simply put an arrow above the vector. Now, if you draw on the reverse way, say for example, you draw a vector from B to A, you call that one position of vector A relative to B because B is the starting point of your vector. So if AB is directed in this manner and BA is directed in its opposite manner, therefore vector AB is the negative of vector BA. Now the coordinates of A is represented by XA, YA, and ZA. So if you try to write the coordinates of A, you have this one, and the coordinates of B is this one. So let's have the coordinate of vector AB. Now, to get the vector AB, it is simply by subtracting the X and Y and Z components or the X, Y, Z coordinates of 2 points which the vector passes. So, to get vector AB represented in 3 dimensions, so we have XB minus XA, or the X coordinate of point B minus X coordinate of point A, then put I boldface plus Y coordinate of point B minus Y coordinate of point A, then J plus Z coordinate of point B minus Z coordinate of point A. Now that's how you write vector AB. Now the rectangular coordinate representation of vector becomes this one. Okay? Then the magnitude of vector AB is simply by Pythagorean theorem. It's the sum of the difference of coordinates. So we have here xb minus xa squared plus yb minus ya squared plus zb minus za squared. The square root of those three terms would be the distance or the magnitude of vector AB. Now, let's have a sample here for 2 dimension to fully appreciate that. We have a vector OA from point O to point A. Now, the slope of this 2D vector is 4/3. And we get that by simply having the slope 8 minus 0 over 6 minus 0, recalling your analytic geometry. Now the magnitude of vector OA is 8 minus 0 squared plus 6 minus 0 squared, because this is the change in x coordinate, the change in y coordinate, and this distance by Pythagorean theorem, we got it by 10 units. And now, if this is 10 units, to get the magnitude of the components of OA, we can use cosine function. So OAX is the x component of vector OA, or the magnitude of the x component of OA, and that is simply OA cosine theta x. So recall that cosine theta x is also equal to adjacent over the hypotenuse. So that is 6 minus 0 over 10. We have it 3 over 5. And that is simply AX minus OX. So the x coordinate of A minus x coordinate of O over the distance of OA, that is said to be the cosine theta, or the direction cosine theta x. We will use this property later on, and also we can see to get the x component, that is simply the direction cosine times the magnitude of the vector. So again, the direction cosine could simply be the change in coordinate about x-axis over the magnitude of the vector. We will apply that the unit vector in the direction of AB can be found by dividing vector AB by its magnitude. So the unit vector in the direction AB is this one. So, unit vector, the purpose of unit vector is simply to give direction. So if this is vector AB, this is vector AB divided by the magnitude of AB represented by D in this figure, we can now have the direction cosine equal to the change in x component over D. And the same case goes for y and z, direction cosine of y and direction cosine of z. And this one for y is simply the change of coordinates about y over d, and zb over z over d. This is simply because cosine is adjacent over hypotenuse. So for theta x, the adjacent side of the triangle is the difference of the x-axis. So for y, the adjacent side of the triangle is the change in y coordinate, and the same case for the z-axis. Now, as you can see, this is similar with what similar to what we have defined previously in this one, where the direction cosine is the change in the x coordinate of O and A, or I mean the change of coordinate of A to O, that is AX minus OX over D, and that's the same in this one. Okay, so now let's try to recall that a vector F, if a vector F acts at AB, so now we can represent vector in such a manner presented this way. So F is equals to Fxi plus Fyj plus Fzk. Or by using the unit vector, so we can rewrite vector F into this one, wherein we show the magnitude of F and the unit vector that describes the direction of vector F. And then expanding this unit vector into this one, we have this one.